My name is Devna Grover, and today I'm going to be talking about continuous liquid-liquid extraction for Lomustine intermediate synthesis. Lomustine is a chemotherapy drug that treats brain tumors and Hodgkin's lymphoma. The drug recently went through a price increase of about 1400%, leaving a lot of patients without the life-saving medication. The primary motivation for the research project is to determine a low-cost manufacturing process. This specific research project deals with the impacts of process parameters on liquid-liquid extraction unit operation in the process. For the experiments, we primarily used 2-chloroethyl isocyanate, which is one of the reactants to form Lomustine intermediate, as our impurity. The experimental extractor design was done in 3 phases, the first phase being solvent screening, where multiple solvents were tested and selected based on their miscibility and extracting abilities. For these set of experiments, we chose water as our aqueous phase and 2-methyl tetrahydrofuran as our organic phase. Then we moved on to our batch extraction step, where we conducted experiments in a batch setting. Once our ideal results were achieved, we moved on to the continuous extractor design, where we used syringe pumps to pump the liquid into a coiled tubing which served as our extractor, and which was further fed into a separator having a hydrophobic membrane separating out the aqueous and the organic stream. The samples were collected over a 30-minute period and analyzed in a high-pressure liquid chromatography. The results from the HPLC were used to calculate percent extraction and partition coefficient to assess the extraction performance. Moving on to the results section, Figure 3 showcases chromatograms for organic and aqueous phase when analyzed in HPLC. In the aqueous phase, we can see a distinct peak at 1.6 minutes that corresponds to 2-chloroethyl isocyanate. But in the organic phase, that peak is not visible, which goes to show that the extraction was successful. To see how successful the extraction was, we calculated percentage extraction and partition coefficient. The percent extraction was calculated by finding the difference between the concentration of 2-chloroethyl isocyanate pre-extraction and post-extraction. And we divided by the initial concentration of the 2-chloroethyl isocyanate and multiplying it by 100. The partition coefficient is defined as the ratio between the concentration of 2-chloroethyl isocyanate in the organic phase and the aqueous phase. We did the experiment for 2 different residence times, and the results are shown in Figure 4. We can see that for the longer residence time, the percent extraction is higher and the partition coefficient is lower, which is ideally the better scenario, as the lower the partition coefficient, the better the extraction, as it is directly proportional to the concentration of 2-chloroethyl isocyanate in the organic phase. Figure 5 showcases the partition coefficient and percent extraction for 3-minute residence time in 3-minute intervals. It showcases that as the time increases, the percentage extraction increases and the partition coefficient decreases. With the percent extraction being 82% and the partition coefficient being 0.36, the results show that the higher residence time of 3 minutes is better for a minimum impurity design. The project can be further expanded into modeling for longer residence times, as well as future simulation work of the end-to-end manufacturing process scale-up. It also gives us an insight about the continuous manufacturing process, which is where the pharmaceutical industry is headed now. This research is funded by the Food and Drug Administration. I would like to thank Dr. Zoltan Nagy for providing me with a platform to pursue this research, and Jaron Mackey for providing mentorship throughout the project. I would also like to thank Eva Zenk and Gabby Prunetta, who made this project possible. This brings me to the end of my presentation, and if you have any questions, I can answer them in the comments below.